Okay, so how is everyone today?
I love the shirt. But is it true?
Well, probably not. I did it. Good. So, last time we were talking about functions and families of functions, and so here we are. We're going to try and summarize the various functions that we know. So the first family of functions is the lines. So these are functions that can be expressed with the formula mx plus b. So f of x is mx plus b, and we will single out three specific cases. One of them, so one case we'll draw here, one case we'll draw here, and one case we'll draw here. So the left case will be the case when m is negative, the middle case m is 0, and the right case m is positive. So now in all cases, without regard to value of m, if you input x equals 0 into the function, what comes out? B comes out, right? Which is to say that it doesn't matter what m is. If you input x is 0, you're going to do m times 0, so that's 0, and then add b, so that's b. So all of them, they all output, at 0, they all output b. For example, maybe for this, in this case, we'll have, x is 0 and y is b. So 0, b. That's one of the points. Now, because I didn't draw a scale, you can't tell me the exact value of b, but from this drawing, you should be able to tell me the sign of b. What's the sign of b? Positive. It's positive. How do you know that b has to be positive? Well, yeah, right. It's above the origin. It's on the positive part of the y-axis. So this is the case when m is negative. So we want to draw a line that's sloping down and to the right. Okay, so then, what I'm saying is here's an example of a line of a function that's mx plus b with a negative m. And it just so happens that it has a positive b. What would a line look like if m is 0? Be horizontal. What value would it be at? Would it be at? Yeah, it would be at b. So here's 0b, and the line would look something like this. Of course, this is a different b than the b on the left. So again, because we didn't draw a scale, you can't tell me the exact value of b, but you can tell me the sign of this b. It's negative because it's on the negative part of the y-axis. All right.
So would it be correct to write negative b in the?
No.
No, because negative b in and of itself, or b could be negative.
Right.
Yeah.
So and in particular, if b is negative, then negative b is positive,
Right.
which is a little disturbing, right? So concerning the phrase negative x, is it possible for negative x to be a positive value? Yeah, when x is negative. So when x is negative 7, negative x is negative negative 7. Which is disturbing but true. All right. So finally, the last case is the positive case. So maybe this is the y-intercept now, 0b. And then now we want to draw a line, and how will it look? It's going to go up and to the right. Okay, so, well, these are lines that slope down, horizontal lines, and lines that slope up. Now, there's actually even one other kind of line that we haven't mentioned. So if it doesn't have, if it's not negative slope, and it's not positive slope, and it's not horizontal, then what's the other conceivable kind of line? Vertical, right? Why? But I refuse. I refuse to include vertical lines in our list. Why am I refusing to include vertical lines? What do you mean it is undefined? I agree. I make no dispute there, but it's still a line, though. But why am I not including a vertical line in this list of functions? Because vertical lines aren't functions, right? Vertical lines aren't functions because they don't pass the vertical line test. A graph is permitted to have at most one intersection with a vertical line, but a vertical line has infinitely many intersections. It would be like a vending machine where you walk up to it, and it's just got one button on it, and you press the button, and everything comes out. Just, okay? It's not a function. Okay, so concerning these three, we want to figure out the domain, the range, the image, whether or not it's injective, and whether or not it is surjective. So for every one of these. So domain, range, image, injective, surjective. Domain, range, image, injective, surjective. All right. What's the domain? In fact, in all cases. The reals, right? Because this is a function defined by an expression. No domain was given. Therefore, the implicit rule is invoked, which is to say that the domain of this function is the natural domain of mx plus b. The natural domain of mx plus b is all reals because there's no divisions and there's no radicals, even radicals, so nothing can go wrong. So for each one of these, the domain is the reals. Visually, you can confirm that because, remember, the domain is a subset of the horizontal axis. So, if you like the paint and mashing analogy, you just take one of these lines and imagine it to be painted in red, like it's dripping wet, and then you mash it onto the horizontal axis. Which parts of the horizontal axis will get colored red? All of them will, for all cases. If you don't like the mashy paint thing, then you can do it with X lines. You ask, well, concerning these vertical lines, which vertical lines have intersection? All of them do. As a result, all points are in the domain. Okay. What about the range? All reals. And why is that? Because it wasn't explicitly given. And in that case, concerning the range, the implicit rule is that if no range is specified, then the range is the reals. And that's analogous. The vending machine analogy is that if we are a vending machine manufacturer, if they don't say what they want installed and on display, everything is going to be installed and on display. All right, what's the image for this one? All reals. How do you see that?
It's the same domain. It has a horizontal line test.
So horizontal line test is the question to ask about injectivity.
All reals can be obtained.
Right. All y values, right?
Y values, yeah.
So again, with the paint analogy, now you want to mash it onto the y-axis, onto the output axis, and ask, well, if it's dripping wet with red paint and you mash it, which points will be colored?
All the points on the y-axis.
Every one of them. And if you don't like the paint thingy, then you can say, well, concerning these y values, for example, this particular negative y value here, does it have an intersection? It does. In fact, all of them do. As a
And it has to be only one.
just one. So this is the image is the reals. Okay. What about for this one? What's the image? Just the point B, right? Just the point B. That is to say, consider this this thing, and it's all the points are painted, and you mash it. Which points get colored red? Just that one, right? If you don't like the paint thing, then you can say, well, concerning this y value, does this y value have an intersection? It does not. How about the ones up here? No. But that one does. So just B. So the image is the set which only contains B. Okay, and what's the image for this one? All the reals. Okay, is this one injective? Yes? Because now the question is concerning those, in the paint analogy, concerning those points that do get painted, is it the case that every point gets painted once? So you mash it, all the points that get painted, they get painted one time. If you like the lines thingy, you ask, well, here, for example, here's a point that has an intersection. Does it have exactly one intersection? The answer is yes, and that's true for all of them. So the answer is yes, because this passes the horizontal line test. What about this one? Is this one injective? So I heard yes and no, and one of these answers is correct. So whatever your answer is, you've got to justify it. So if yes, why yes? So so which one is it? It's no. Why is it no?
All the numbers.
Well,
Because that point passes through the y-axis more than one time.
okay. So like for example, the horizontal line test, you could say it like this. Every horizontal line must intersect at most once. So here we have 0 intersections. That's nice. In fact, everywhere down here we have 0. Everywhere up here we have 0. How many intersections do we have right there? How many times does this graphite line touch the red line? Infinitely many times. Right? Right? They're touching everywhere. Right? That graphite point is on top of that red point, that graphite point on top of that red point, that graphite point on top of that red point. No intersection, infinitely many intersections. How many intersections are permitted? One. Right? So in a sense, this is like kind of like the exact opposite of injective. Right? It could not be. It couldn't be any less. It would be. It's like a vending machine that has infinitely many items in it and infinitely many buttons on it. But in fact, every button gives you a broccoli. Right, every single one of them. So if someone walks away from that machine with a broccoli, do you have any information about what button they may have pressed? None, right? So this is the least injective function conceivable. So no. Is it injective? No, never mind. I just asked that. And then how about this one? Is this one injective? Yes, because again, every horizontal line intersects at most once. So yes to this one. So how about the question of surjective? How do you address that here? So vertical line test is it answers the question of whether or not what we're looking at is a function.
For surjective, that means the range has to equal the image.
Right. Is the range the image? Which is to say, you could say it like this: is every item in the range achieved at least once? So, but as an equation, the question is it the case that the range is the image? And the answer is yes. Yes, because the range is equal to the image. you know, because the range is all reals and the image is all reals. How about this one? Is this one surjective? No, right? It's not, because the range is all reals and the image is just B. So that's like a vending machine where every conceivable candy bar is on display, but you can only get, you know, what's a bad candy bar? They're all pretty good. You insert in your own estimation what a bad candy bar is. You only can get that one. So the answer is no, because the range is not the image. How about this one? Yes, because the range is equal to the image. Okay, the next family is the power family of functions. That's how we'll call it. It is functions that have the pattern f of x is x to some exponent n, where n is 1, 2, 3, 4, etc. Okay, so we're going to draw 4 examples. So I'm making the axes small and close enough to where I could make 5 of them, but I'm just going to make 4 of them. And the reason is because I'm going to make another 4 a little bit lower on the page, but they're going to be over here, if you're just trying to duplicate what it is that I'm doing. Okay, so then they're all going to look like f of x is x to some exponent, so f of x is x to exponent 1, f of x is x to exponent 2, f of x is x to exponent 3, and f of x is x to exponent 4. So I'm going to write the exponents in red just so you can see what part of the pattern is changing. Of course, normally you don't write exponent 1, but I'm writing it just to emphasize. So this first one, f of x is x to exponent 1, that is in fact a line with slope what? What is m? 1, right? Because this is 1x, and then what's its intercept? 0, because it's plus 0. So this is 1x plus 0. So in fact, this particular one that we're about to draw belongs to both families. So it looks like this. It's a line of slope 1 through the origin. F of x is x squared is a parabola. We've done that a lot, so I'll just draw it quickly without apology. It looks like this. X cubed we did last time, so I'll draw it quickly. It is like the parabola a little bit, but instead of it being a cup like a parabola, it is like the left side has been twisted down, so that it looks like that. Okay, so that's the visual thing, but why should it visually have this behavior? Why does it look this way? Alternatively, why is it not like the parabola? Why is the parabola like this with both arms up, and the cubic like this with the right arm up and the left arm down?
Because of the possibility or lack of possibility of y values that are negative.
Okay, I agree. So I think you're telling me that this one can or cannot
have negative y values.
Okay, this one cannot produce negative y values, but this one can.
Correct.
Why?
Because an even root or an even exponent cannot yield a negative result.
I agree. So, for example, you take negative 5 and square it. Well, the negatives cancel and you get 25. So even though the input was negative, the output is positive. But if you take negative 5 and cube it, then the first two negative 5s will give you positive 25, and then you multiply by the last negative 5, and you get negative 125. So a negative input results in a negative output. Okay, so now I want you to speculate, because we've never seen this one before. This will be the first time. My question is this one, it's going to be like one of these two. Which one is it going to be more like?
First square.
Like this one. Why like this one?
So you want
Right, because it has an even exponent. As a result, the outputs must be non-negative.
would it be wider though? I mean, theoretically, I know this is just pictures.
So what will happen is that near the origin, it's going to be flatter. It'll be like someone took the parabola and hammered on it until it was flatter near the origin. Away from the origin, it's going to be much steeper, as if someone hammered it, going all the way up and made it steeper. The reason is because, for example, if you square 10, you get 100. But if you do 10 to exponent 4, you have 10,000. Right? So then, what I'm saying is that for this one, by the time you move over to x is 10, you're at height 100. But for this one, by the time you move over to x is 10, you're at height 10,000. So it's going up pretty quick. So it's kind of flatter near the origin. It's not exactly flat, but my drawing skills are only so excellent. All right. So I'm not going to draw it, but let's talk about it just briefly. The next one in this sequence would be x to 5. Concerning its overall shape, would it be more like this x squared or more like x cubed? Be more like x cubed in the sense that one arm would be down, the left arm would be down and the right arm up. But it would be sort of like x to the 4 in the sense that it would be becoming quite flat near the origin and quite steep away from the origin. At any rate, what I want you to see is that all of the odd ones will have this property, that the left arm is down and the right arm is up. And all of the even ones will have the property that both arms are up. Now, for each of them, let's write down the domain, range, image, whether or not they're injective and surjective. So what's the domain for, in fact, all of them? The reals. The reals because there's no restrictions. Because there's no divisions by 0, and there's no even radicals, so there's no restrictions. What's the range, in fact, for all of them? The reals because no range was made explicit. As a result, the range is everything. Here's the interesting question. What's the image for this one? The reals, right? Which is to say that in the mash analogy, you take these and mash it. Which y values get colored red? All of them do. Or, if you like the lines analogy, which lines have intersection? All of them do. So the image is the reals for this one. What about for this one? Greater or equal to 0. Very good. Because no negative output can be obtained. The next one? Well, everything. The next one? Same as x squared. Okay, good. Is this one injective? Yes. How can you see it? Horizontal line test. Is x squared injective? No. How can you see it?
2 points at the same.
Right, 2 points at the same height. Or, if you like, with the mashy thing, mash, some of the points get colored twice. That one gets colored once, but all the rest of them get colored, that do get colored twice. So here the answer is no, because it fails the horizontal line test, or whatever reason you care to give. Is this one injective?
Yes.
Yes? And the next one? No. Right. So I'd like for you to observe that, again, this pattern is going to continue forever. Yes, no, yes, no, yes, no, yes, no, depending on the parity, even or odd. Similarly, the image is going to be reals, non-negative reals, reals, non-negative reals, all the way down the line. Fine. Is this one surjective?
Yes, the first one is.
Yes, the first one is surjective. Because again, the question is the range equal to the image? And the answer is yes. How about this one? Is the parabola surjective?
No.
No, it is not. It is not because, remember that, how this works. The range and the image are vertically oriented sets when you draw them, typically. So in this case, the range is all the reals, right? It's everything that's conceivable, whereas the image will look like this. So the range is all of this, whereas the image is just this much. And the question is are those two sets the same set? The answer is no. So those are not the same. Is this one surjective?
Yes.
Yes. This one? No. The next one?
Yes.
Yes. The next one? No. Good. Any question about this one? Okay. The next family is the radicals. That is to say, functions that have the pattern f of x is the nth root of x. But the way the definition of radical goes, what's the least radical number? 2, right? 2, and that one corresponds to square root, right?
Yeah.
Then the next one is cube root, and then the next one is fourth root. So they start at 2, which is why I did 4 here, and now I'm going to do 4 here, so that they vertically line up. Okay, so then this will be f of x is radical x, 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 starting with 2, so 2, 3, 4, 5. So, of course, under normal circumstances, when you're writing square root, you don't write the 2. But I'm writing the 2 just to make sure that the pattern is as evident as possible. So we've done square root at least twice now, so I'll just draw it without apology. It looks like this, more or less. Why did I not draw anything on the left side?
Negative brackets squared.
Right.
Negative numbers.
Right. The left side would represent what happens when a negative input is provided to the square root. Well, they're nothing, right? Because that's not permissible. It's not part of the domain. Okay. So the cube root, we also did that last time, so I'll draw it. So it looks like this. So notably, cube root, its plot is on both sides of the axis. That is a visual manifestation of the fact that cube root can accept negative inputs and positive inputs, and 0. So what I want you to see concerning these two is that if you were to grab this cubic and grab it and manipulate it so that you could get this arrow to line up with that arrow and place them on top of each other, it would fit, right? You could take this one right here, grab it, give it a twist, and put it on top of that one. It would work. Now, if you were to attempt to do the same thing with the parabola, take this arrow and make it line up with that arrow, grab this one, give it a twist, and put it down, then you'd see this other bit coming down here. But you can't do that. Why not? Because, well, because then, you know, this plot only includes the red, but suppose, for the sake of argument, momentarily, that it includes the red and the graphite. Would the resulting plot be the plot of a function?
No, no.
It wouldn't be, right? It wouldn't be because it wouldn't pass the vertical line test. As a result, square root, this part of the square root corresponds only to the right side of the parabola. It does not correspond, there's no correspondence to the left side. Whereas cube root, the correspondence is entire. Right? This corresponds to the right side of the cubic. This corresponds to the left side of the cubic. Okay, how will fourth root look? It'll be like square root in the sense that what?
It only has values to the right.
Very good. And then it'll be like the cube root in the sense that near the origin, it's going to be quite flat. Okay, good. And then there's no counterpart above this one, but I claim you should be able to tell me what it looks like, more or less. What does it look like? It's going to be like cube root in the sense that it has both sides. But it's going to be like fourth root in the sense that it's starting to become quite flat. Okay, good. Let's quickly write down these: domain, range, image, injective, surjective. So the even ones will all be the same. What's the domain of all the even ones?
It's positive real x greater than 0, greater than equal to 0.
Right, that one. So 0 to infinity, including 0. Mathematicians will, when we're talking amongst ourselves, we'll call that the non-negative reals. But that doesn't actually work so excellent when you're talking to non-mathematicians because, well, the more negations there are in a speech, the more difficult it is to follow. All right, what's the range? The reals, because no range was specified. What's the image? 0 to infinity. All the reals are on display, yet it's only possible to get these. Is this injective? It is. It is because every horizontal line intersects at most once. Is it surjective? The answer is no, because the range is the reals, but the image is only those reals that are greater than or equal to 0. All right, good. Notably, I'd like for you to observe, I'll skip the cube root for a moment and look at the fourth root. What are the answers to the fourth root? Same as the square root. So the same as square root. In the end, the reason is because this is all even ones will be this way. Okay. Concerning the odd case, what's the domain? Reals. The range. The reals, because nothing was specified. The image. The reals, because everything is obtainable. The reason why everything's obtainable, again, with the paint analogy for this one, is that if this is covered in red paint, and then you mash it, which y values will get colored? All of them will. And if you don't like the color, the paint thingy, then do it with these lines. Notice that there's intersections for negative y values, for positive y values, and also for 0. So every y value is obtainable. All right. Is it injective? Yes, because every horizontal line intersects at most once. Is it surjective? Yes. Okay, what are the answers to this one? The same as the cube root. Good. Any question about these? This pattern continues. So, the kind of thing I might ask concerning this is something like, well, what if I just hit you with a plot that looks like that? And no other context. And I said, which is most likely to be the function corresponding to this plot? Is it more likely that this is f of x is x to exponent 11, or f of x is x to exponent 18? Sorry, that's not right. Is this more likely to be the 11th root of x, or is this more likely to be the 18th root of x? The 11th root of x, because this has the odd behavior. I don't mean odd as in strange, I mean odd as in parity. Good. So another family. The reciprocal family. That is to say, functions that have this pattern. F of x is 1 over x to exponent n for n equal 1, 2, 3, ... So, again, we'll make 4 examples. But we don't need to line them up like we did on the previous page. So f of x is 1 over x to 1. F of x is 1 over x to 2. F of x is 1 over x to 3. And f of x is 1 over x to 4. All right. Well, of course, under normal circumstances, you don't write exponent 1, but I just wrote it there just so the pattern is clear. We did 1 over x last time, so I'll just plot it. So that's what it looks like. This shape is common enough and important enough to have its own name. The name of this shape is hyperbola. And the bola, part of its name, is the same bola as parabola. The shapes, there's a whole family of shapes that go together. Parabola and hyperbola are part of them, but we're not really going to talk about it in our class. But for those of you who just want to know what that's about, like on Wikipedia, the name of that topic is called conics. Fine. We also did this one last time, so I'll plot it. So it's going to be like, how is it going to be like this one? Well, it's still going to have this crazy behavior at 0. So this crazy behavior is like, conceptually it's happening because you're getting near a division by 0. That's why it's losing its mind here. Yeah. So, but because this is being squared, even if the input were negative, it's going to be squared. So, in a sense, turned into positive. So it's going to be like this one, but it'll be like, yeah, like flipping this side up. So like this. But besides flipping the left side up, there's another difference. So the other difference is that this shape right here, this kind of boomerang shape, an infinite boomerang, right? Because it goes all the way that way, getting pointy, and all the way that way, getting pointy. It's symmetric on either side. Whereas this one is not symmetric. It would be like, if you can imagine, that all this region in here is full of toothpaste, and you give it a squeeze, and you've squeezed most of the toothpaste out of that one. It's not symmetric anymore. So in fact, there's an infinite amount of area on both sides for this shape. But for this one, there's an infinite amount of area in here, but the area in here is now finite. Not that that matters for our class, but it's interesting to think about what that might mean. That means that, so in particular, you could paint this side, but it would not be possible to paint this side. Okay, good. How about this one? Will this one, 1 over x cubed, will it be more like the 1 over x to 1 or more like 1 over x to 2? Right. In the sense of up and down, it'll be like this one. But in the sense of flatness, squeezedness, it'll be like that one. So it's not exactly vertical, and it's not exactly flat, horizontal. But it is much more so than this one. Finally, x to 4 will be like x to 2 in the sense of up and down, and it'll be quite flat. Good. So now let's quickly do the domains and do the domain dance. So domain, range, image, injective, surjective. So how about the domains? The domain is the same for all of them. What's going to be the domain? Not all reals. Yeah, everything but 0, right? Because, well, you can't divide by 0. So I'll just to make it very as succinct as possible, I'll say x not 0. So anything but 0, anything but 0. For the first two, I'll write it. How about what's the range for the first one? All reals. All reals because no range was specified. And the second one, the reals. So when you said no, I suspect you meant your response was actually to the next question, image. So what's the image? Right, everything but 0 for this one. Because, you know, if you do the paint thingy and say, okay, it's covered in paint and now I mash it, which points get painted? Everything but the origin. Right? The origin can't get painted because, you know, what point would go to it? There isn't one. Alternatively, notice that all the negative y values have an intersection. All the positive y values have an intersection. But that does not have an intersection. Yes?
For the second one, why is the range all reals if they don't go below 0?
Because the rule for the range is that if the range is not explicitly specified, the range is all reals. The question that you I suspect meant is about the image. So I'll ask you directly then. For this one, what's the image? 0 to infinity. So this one is anything except 0, whereas this one, we only positive things. Okay, so how about this one? Is it injective?
No, it doesn't pass a horizontal line.
Okay, please explain.
There's no line that passes through 0.
The range hasn't matched it.
At most.
Right. The injective
yeah.
the injective test is 0 or 1.
Yeah.
So you know, you got to be kind of, it can be kind of difficult to keep track of when is it at most once, when is it exactly once, and all that. So you can say that something is injective when every horizontal line intersects at most once. Now, if a horizontal line, that means that the number of permissible intersections is 0 or 1. If the number of intersections is 0, that means that that point in the range is not in the image. So another way to say, is it injective, is to say, concerning all the points in the image, do all of them get painted exactly once? And well, in this case, the answer is yes. So all points that do get colored once. All points that do have intersection have one intersection. So this one has no intersection. That means it's not in the image. To make the vending machine analogy, that would be like saying, is it the case that every item that can be retrieved from exactly one button? You know, we're not worried about if that Snickers can't be retrieved at all. Okay, good. So is it injective? The answer is yes. Is it surjective? The answer is no. The reason why the answer is no is because the range is not the image. The reason why, to hopefully make it, hopefully keep it clear, is that for this first one, the range is everything, whereas the image is everything except 0. And then, are those the same? They're not the same, so it's not surjective. All right, how about, is this one injective? No, right? Why is this one not injective? Right, because notice that particular y value has 2 intersections. So the answer is no for this one, because it fails the horizontal line test. Alternatively, you could say, notice that for this one, for 1 over x squared, if you plug in 4, you get 1/16. And if you plug in -4, you also get 1/16. So if someone walked away from this vending machine and they were walking away with a 1/16, would you know for sure which button they pressed? You would not know, because there'd be 2 possibilities. As a result, this is not injective. Is this surjective? It is not. Again, because the range is everything, but the image is only the top half. What's the answer? What are the answers to this one? Right, this is the odd case, and this one, the even case. And it just continues. These happen, this kind we know and love in our human experience, though you may not realize it all of the time. It might not be forefront in your mind. But like, this is the way gravity works. Inverse square. So we love that. This is what happens when you take something that's like gravity, inverse square, and you sum it up a lot. Then it looks like that. So these happen all the time. The further you get to the right, the less likely they are to happen in nature. That's my experience. Like, I can't think of anything that behaves like 1 over x to 5. Last thing is, besides functions like that, we can have functions like this. How about f of x is 13x plus 14 when, I don't know, 5 is less or equal to x is less than 8, and it's equal to x squared when x is more than 42. All right. So we've seen functions like this before. This is called a function defined by clauses, or a piecewise-defined function. The last time we saw this was when we were talking about absolute value. and we named these clauses 1 and 2. There could, in principle, be as many clauses as you wish. So I'll leave us with the following questions. What is f of 6?
13 times 6 plus 14.
How do you know that?
Because the value for it is fits in number 1.
Right. So the question is, the input is 6. Is it this kind? The answer is yes. So here we need to use clause 1. So it would be 13 times 6 plus 14, whatever that happens to be. What about f of 20? What about that?
Second
X, or no, yeah, it's x squared. 2x is not greater than 42. It's undefined.
Yeah, this is undefined. Because the question is well, concerning these clauses, which one of them does it fit? None of them. Okay, then how about f of, say, 50?
That is 50 squared.
Yeah, that'd be 50 squared. Because that matches the second clause. So, as a result, we can say that the domain of f is the union of those two clauses. 5 to 8, union 42 to infinity. All right, so have a nice Wednesday.